Okay, welcome to our face-to-face meeting today for STAT151. We are going to talk about some questions that were posted to the discussion board about the homework mostly from sections 2.4, 2.5, and 2.6 that talk about the binomial, negative binomial, and Poisson distributions. The first question I want to talk about comes from section 2.4. Section 2.4-18 is the problem. This is the one that asks about a blood sample taken from n individuals, and part of each sample is going to be put into a common pool. The other part will be saved. They test the pooled sample. If the pooled sample is negative, then they stop and they don't do any more testing, and they conclude that all of the individuals are negative. If the pooled sample tests positive, then they go through and they test all of the individual samples from the n people. So we are interested in this case in the number of tests that we expect that will be needed. So here, just to kind of keep in mind, the number of tests, there are really two possibilities. If we consider y is the number of tests needed, then there are two possibilities. Y could equal 1, in which case all of the individuals are negative for the disease and that pooled sample test negative. Or Y could equal n plus 1, where they would test the pooled sample and then have to do the n individuals also. Now for the particular example that they're looking at here, they say to assume that the probability that a person has the disease is 0.05, and that there are n equals 5 individuals being tested. And we want to compute the expected number of tests needed. So in this case, again, if y is the number of tests needed, here the sample space, the support of y, is 1. And then 5 plus 1 is 6, so there could be either 1 test or 6 tests done. And in order to find the expected number of tests, the expected value of y, we need to figure out the probability that y takes on each of these two values. Now, keep in mind the probability that y equals 1 is the same as the probability that all are negative. We can find the probability that all of the tests are negative using the binomial distribution. If x is the number of individuals who have the disease, x has a binomial distribution with n equal to 5, because there are 5 individuals, and p equal to 0.05, because there's a 0.05 probability that any individual person will have the disease. If we're willing to assume independence from person to person, then we have this binomial distribution. So the probability that y equals 1 is going to be the same as the probability that x, our binomial random variable, is equal to 0. Can use similar kind of logic to find the probability that the number of tests is equal to 6. And then once you've done that, to find the expected value, expected number of tests, we're going to sum over the support of y, our y, times the probability that y takes on that value. So hopefully that'll get you on a good start to working through the rest of this problem. The next homework question that I saw questions about was section 2.5, problem number 1, We're told that an excellent free throw shooter attempts several free throws until she misses. If P is equal to 0.9, which is the probability of her making a free throw, we want to know the probability of having the first miss on the 13th attempt or later. In order to answer this question, we're going to assume that her free throws are independent of each other. Otherwise, we really don't have enough information to solve the problem. So when we are looking at the number of tries at something that we need in order to have the first success, that has what's called the geometric distribution. So let's consider X is the number of shots, and we're interested in the first miss until her first miss. So miss here is going to be success. Because geometric distribution, we're looking at the number of trials till the first success. So till the first miss, that means we're calling the miss a success here. So then the probability of success we're told the probability that she makes a shot is 0.9, which means the probability of success, missing, is 0.1, 0.1. Now last week I talked about finding cumulative probabilities and probabilities that X is greater than a particular value with a geometric distribution. But essentially what this comes down to is the probability that it's at least 13 shots until she misses is the same as the probability that she makes the first 12 shots. So that's making 12 shots in a row with a chance of 0.9 of making each one. So it's 0.9 times 0.9 12 times, so 0.9 to the 12th power will give us our answer for that part. Now for part B, if she's going to now continue shooting until she misses 3 shots, we want to know the probability that the third miss occurs on the 30th attempt. When we're looking for a particular number of successes, and we're going to stop after we get to that point, then we think in terms of the negative binomial distribution, where R is the number of successes and P is the probability of success on each trial. So in this situation we're looking for the third miss, so R is going to be 3. Since we're going to misses, again, success would be a miss here. So our P, the probability of a miss, should be 0.1. And from there, we can use the probability mass function for a negative binomial distribution to calculate the probability that, if we call Y, the number of shots until the third miss, to find the probability that Y equals Y. Sorry, Y equals, well, we can use the negative binomial PMF to find the probability that Y equals Y, and if we substitute in, we can find the probability that Y equals 30. So again, hopefully this will help you get on the right track. I think that sometimes what's confusing about this problem is that they tell us that P equals 0.09 is the probability that she makes a free throw. And we're used to seeing the way that the probability mass functions are written, P is the probability of success. In this case, the P that they're giving you here is the probability of failure, not of success. And so we need to find the complement, 1 minus that, in order to find our probability of success to use in our probability mass function model. Okay, next homework problem. 2.5-10, red rose T, places one of 12 figurines, they're chosen randomly, in each box of T. We want to know how many boxes of T on average we need to purchase until we have all 12 figurines collected. This one is very similar to example 2.5-5 on page 78. The idea here is that we're going to be applying a geometric distribution to answer this question. We know that first box of T we buy and open up, the figurine is definitely going to be one we haven't seen before, so the expected time to get the first figurine, so if we call x1 the number of boxes to get the first figurine, we know that the expected number of boxes to get the first one is definitely going to be 1. Right? Now, if we call x2 the number of boxes after we collect the first until we collect the second one that we haven't got, we're looking till the time until the first new figurine. This has a geometric distribution with P equal to, now there's 1 out of the 12 that we already have had, so there are 11 out of 12 that we haven't. And so the expected time it'll take after we've got the first one, expected number of boxes till we get the second one, is going to be 1 over P, which is going to give us 12 over 11. Now the time to get the third figurine, number of boxes after the third figurine, after the second figurine was collected and until the third, this is again going to have a geometric distribution, but now our P is different. There are 10 out of 12 figurines that we haven't already collected. The expected value of x of 3 is 1 over our new P, which is 12 over 10, and we can continue this process. As I say, it's very similar to example 2.5-5, so take a look at that if you're having trouble. The last of the homework problems that I saw questions posted about was 2.6-13. This is one that says a policyholder is 4 times more likely to file exactly 2 claims as to file exactly 3 claims. We're supposed to assume that the number of claims filed follows a Poisson distribution, and we need to determine the expected value of x squared. So here x is the number of claims filed. We're told to assume that x has a Poisson distribution. Poisson distribution would be characterized by the parameter lambda, which is the average number of claims filed in a unit of time, but we aren't told what the value of lambda is, so we're going to have to figure it out. The way we can do that is by using what we know. We're told that a policyholder is 4 times more likely to file exactly 2 claims as to file exactly 3 claims. We can use our probability mass function for the Poisson distribution, which is f of x equals lambda to the x e to the minus lambda over x factorial. So this is f of 2 equals 4 times f of 3, and I can substitute in lambda squared times e to the minus lambda over 2 factorial is going to be equal to 4 times lambda to the 3rd power times e to the minus lambda over 3 factorial. Now I should be able to solve and find lambda, and once I have lambda, I can use what I know about the mean and variance of a Poisson distribution to find the mean and the variance. And then using the fact that the variance is the expected value of x squared minus the mean squared. If I know the mean and I know the variance, I can solve for the expected value of x squared. So hopefully that helps get you started. All right. The last thing I wanted to do today was just show people how to use the calculator to calculate probabilities with the binomial, also with the Poisson and the geometric distributions. They're built into the TI 83, 84. If you don't have a TI 83 or 84, it's okay, but for some people who do, I wanted to show you how you can work with that. And there are also the tables in the back of the book that people can be working with that show cumulative probability dense distribution functions, and also there's the online applets that I had a link to, but for people who want to use the calculator, I wanted to show people how. So for the binomial distribution, remember that we are interested in the number of successes out of n independent trials. And P is the probability of success for any individual trial. If we want to calculate the probability that x takes on exactly the value little x, we can use the calculator function binomial PDF, and we enter our n value, our p, and our x. So for example, if I want to find, if I have, going back to, say, the chance that I would have 3 heads in 4 coin flips, x would be the number of heads, n is the number of flips, so I'd have 4 flips. P, assuming the coin is fair, would be 0.5. The probability that x equals 3 I could find by using the binomial PDF, putting in n for p, 0.5, and x would be the 3 heads. So to do this, I'm going to go to the distributions, so I need the second key, and then this vars, above vars it says distributions. If I scroll down to the binomial PDF, press enter, I can enter my values, 4, 0.5, 3, and it gives me my probability, 0.25. If instead I wanted to find the probability of 3 or fewer heads in 4 coin flips, I'd be calculating the probability that x is less than or equal to 3. To do this, I can use the binomial CDF. Cumulative is what the C is for. I put in again my n, 4, my p, 0.5, and my value, x, 3. And I just need to scroll down a little farther to get there in the distribution list. Binomial CDF, n is 4, p is 0.5, x is 3, and it gives me 0.9375. So it just saves us from having to do a lot of calculations. by hand, if we can do this. So again, the probability that x is equal to x, we use the binomial PDF. If we want to find the probability that our random variable x takes in a value less than or equal to little x, we use the binomial C for cumulative distribution, N, P, and X. We can do the same kind of thing with the Poisson and the geometric. For the Poisson, remember our parameter is lambda. So if we want to find the probability that x is exactly equal to a particular value, then we can use the Poisson PDF. We enter our lambda value and our x value. If we want to find the probability that x is less than or equals to some particular value, little x, we use the Poisson cumulative, so CDF, and enter our lambda and our x value. Just like we did there, we just have to scroll down again just a little farther in the distribution list. There's the binomial, there's the Poisson, the PDF, and the CDF. And then there's also the geometric PDF and CDF. The geometric distribution is parameterized by the probability of success on each individual trial, P. When we want to find the probability that it takes exactly a particular number x trials to have our first success, we can use the geometric PDF. We need to enter our P value and our x value that we're interested in here. And if we want to find the probability that x is less than or equal to a value, little x, less than or equal to, we're thinking cumulative, so C, D, F, and we enter again our P, probability of success on a trial, and our x. And again, you can see there, just scroll around in here. There's the geometric PDF and the CDF. And you're welcome to use the calculator on your homework. You're welcome to use it on the test if you like to. If you do, I strongly suggest, as you're showing your work, showing me which calculator function you used and what you put in for each of those values, so that if your answer is not correct, I can tell where you went wrong and also give you potentially partial credit. So please make sure you do that. Okay, the last thing I just want to mention is that we do have spring break next week. I will be posting review materials for the midterm before spring break, but the module doesn't technically start until we get back from spring break. So that week on Thursday, you will have your midterm. It's proctored. You can either take it on campus or you can take it using the ProctorU online proctoring center. So please, if you haven't looked through and decided what you're going to do, start thinking about how you're going to take the exam, whether you can make it to the on-campus date or if you are going to do it through ProctorU, you need to start making a reservation. So I'll, as I say, put up the review materials and let you get started, but no pressure. If you want to take the week off, you have the week off. Have a good day.